In this video, we will discuss the death of a low-mass star similar to our Sun. For stage 8, it's the subgiant branch. At this point in time, the hydrogen has been depleted in the core of the star. And this means that the fusion is going to start to move outward around the core and is going to actually take place in a shell that surrounds the core. This will cause an increase in the temperature in the layers around the core, which will increase the pressure. In order for the star to stay in equilibrium, hydrostatic equilibrium, it's going to have to expand to overcome the increase in pressure. As it expands, it's going to become more luminous, but it's also going to be cooler. The surface temperature is going to drop at this point to about 4,000 Kelvin from the 5,000 to 6,000 Kelvin that we have originally. Okay, at this point it becomes a red giant, and we call this, again, stage 8, the subgiant branch. Okay, as the hydrogen is depleted in the core, it starts to burn in a shell around the helium core. The temperature reaches about 100 million Kelvin, but it also gets up to about 500 million Kelvin initially. Okay, at that point, the helium can actually start to fuse into carbon and oxygen. So now keep in mind that this picture is inside a 5 solar mass red giant compared to the Sun. But you can see what's taking place. Here you have the hydrogen being converted to helium in a shell around the helium core. And notice that that's very small compared to the rest of the size of the Sun, or the star in this case. Okay, next we move into stage 9, the helium flash. This involves quite a bit, and it doesn't happen immediately. But what we do have is that the luminosity is many hundreds of times the solar value. So our Sun becomes hundreds of times brighter. Okay, the radius becomes about 100 times the original size of the Sun. The helium flash takes place with the following characteristics, and you might want to take note of these. There's no rise in pressure. There's no expansion of the gas. The nuclear reaction rate increases. So the temperature increases rapidly, but because there's no rise in temperature, you end up getting this runaway explosion, okay? Once that explosion takes place, poof, the pressure and the gravity are again balanced, and you then have a stable star again. So let's take a look at this on the HR diagram. So as you can see, you're only going to have a helium flash for stars between the size of our Sun and maybe 3 times the size of our Sun. Anything larger than that, you're just going to end up with the death of a large mass star. You might end up fusing heavier and heavier elements and not have that helium flash at all. Okay, so stars smaller than our Sun will never be able to fuse helium to carbon. Stars more massive will fuse helium into carbon and oxygen without having that explosion take place. Okay, once the gravity and pressure are in hydrostatic equilibrium, the star moves to the horizontal branch. This is slightly above the main sequence. 20 to 30% of the original stellar mass may escape during this period. The helium will actually burn in the core and be converted to carbon and again oxygen. Eventually, though, what's going to happen is that carbon core is going to be all that's left. The central temperature at this point reaches about 200 million Kelvin. Once the helium has fused to carbon in the core, the helium will begin to fuse in a shell around the core, and the hydrogen will continue to fuse in a shell surrounding the helium and the carbon core. So this ends up bringing us to stage 11, the red supergiant. The star is going to be cooler as it expands due to the fusion that takes place in the outer layers. That's what causes it to expand. So here we still have our hydrogen shell burning. Now we add a helium shell to burn out around that carbon core. And again, the central region of the star is the carbon, which is millions of Kelvin in temperature. The surface temperature is only about 4,000 Kelvin at this point. And then it enters it goes up higher on the HR diagram. So let's take a look at this. So here you can see we have the carbon core, we have the helium fusion shell, and we have the hydrogen fusion shell surrounding that. Okay, so let's take a look at the HR diagram for this. Here you can see the star moving off of the main sequence as it burns hydrogen around a helium core. Here you can see the helium ignition, which is your helium flash. And then you can see that it moves to the horizontal branch. And then from the horizontal branch, it's now burning hydrogen in a shell and helium in a shell around a carbon core. And so you can see the path as it moves off of the main sequence, it goes up, and then it goes horizontally to the left. So the temperature increases. And then you can see that the temperature decreases, and then the luminosity gets even brighter because this star is now getting much, much larger. As the hydrogen continues to burn in the shells, the internal temperature rises to about 300 million Kelvin, and the surface temperature rises to about 100,000 Kelvin. The burning becomes unstable, and an envelope which surrounds the core of the star continues to expand and cool. It actually becomes unstable. At this point in time, with all of these layers burning and expanding, contracting, expanding, contraction, what we have is this, the radius of the star oscillating more and more violently. As this continues to happen, eventually what's going to happen is the gas that's surrounding the star, all of that hydrogen gas that's around the star, is going to actually explode outward or be ejected outward. Okay, and this is what we call the planetary nebula, the carbon core planetary nebula. Right before this happens, the surface temperature goes from about 100,000 Kelvin to about 3,000 Kelvin. Eventually, though, what's going to happen is that this gaseous material that's glowing is going to move away from that core. The core, remember, is still 300 million Kelvin, so it's still very, very hot. Okay, so this forms our planetary nebulae. I want to show you a couple of pictures of some planetary nebulae. This one on the left is the Helix nebula, or nebula, sorry. I always think of it looking like an eye. It's really kind of freaky. So here again, you can see the gas has been ejected. And we never really know how it's going to be ejected. Sometimes it's a spherical ejection. Sometimes we see crisscrossing envelopes ejecting. If you look at the picture on the right, at the very center, you can see a bright dot, and that is your core, the core of the star. Here are two more pictures. And here you can see the difference in how they look compared to the other two. And so they're all quite unique. Eventually, the ejected gas will dissipate and only the core will remain. This is what we call a white dwarf, and this is where we have stage 13. Its central temperature is about 100 million Kelvin, and the surface temperature cools down to about 50,000 Kelvin. So at this point, the shell has dissipated, the core continues to glow, the central temperature is still the temperature of the core, 100 million Kelvin, but the rest of it has started to cool down and it's only about 50,000 Kelvin. This puts it at the O spectral class. Okay, as that core continues to cool off, eventually we won't see it anymore. It will stop glowing. It will reach a temperature of space, about 3 Kelvin, and that means that it will become a black dwarf. So again, the central temperature will be about 3 Kelvin, close to 0. Same thing with the surface temperature. Here's a neat little tidbit of information. We have not seen a black dwarf yet because none of these stars have been around long enough. Our universe isn't old enough to have produced a black dwarf. That's how long it takes for these things to cool off. So it's quite incredible that we haven't seen a black dwarf yet, and we won't for quite a long time. Okay, so we can see how the stars move on the HR diagram from stages 11 to stage 14. So let me show you this. Okay, so the star is at the supergiant and giant region of the HR diagram for stages 11 and 8 respectively. The star then moves to the upper left-hand side of the HR diagram. The planetary nebula as shown as a solid white dots on the diagram. The star then moves down towards the right as a planetary nebula becomes a white dwarf. The black dwarfs move completely off the HR diagram. They are no longer visible. And again, we don't have any black dwarfs yet. Okay, so you can see this whole process. Here's your main sequence. They move up to the giant, then they move to the horizontal branch, then they move to supergiant, and then they become a planetary nebula, and then as they drop down, they become a white dwarf. And you can see that they get so hot that it is difficult to plot them on a normal HR diagram. The color panel you see on the right is your typical HR diagram. Okay, so here again we show you the stages by number. Number 7 is the main sequence star. 8 is your subgiant branch. 9 is your helium flash. Then 10 is your horizontal branch. 11 is your super red giant. 12 is your planetary nebula. 13 is your white dwarf. 14 is your black dwarf. And again, we've never seen a black dwarf. Okay, so what proof do we have? So here's the evidence. We actually look at globular clusters. This is actually M5. And what we do is we plot all of these stars in the cluster because they're all the same age. So you may say, well, wait a minute, how does that work? They're all in different parts of the main on this diagram. Well, if they're more massive, they're going to die faster. If they're less massive, they're going to die later. Okay, so the time it takes to move off of the main sequence decreases the larger the star is. So because they have different masses, you're going to be able to see the entire evolutionary track with these stars. So if you look carefully, you'll see stars on the main sequence stars are your yellowish stars. Then you see them pulling off to the upper right-hand corner where the red supergiants. And then you can see them moving all the way to the left. Those bluer stars are going to be your planetary nebulae. And so you can see almost the whole evolutionary process when we look at these globular clusters. And again, the globular clusters are all star material that was made at the same time. It's not gone through the evolutionary process like our solar system has. Our solar system has probably gone through 2 or 3 iterations of star life or supernovae to form us, whereas a globular cluster is all formed at the same time.